Good afternoon and welcome to Hydromantis webinar. Today we are going to talk about modeling of nitridation and NMOX processes in GPSX. These processes are also known as deammonification process. My name is Rajiv Goyal and I have my colleague Spencer Snolling here with me, and we will be conducting this seminar together today. So the topics we are going to talk about today is the process background, just to give you a little bit of background about deammonification process and why we are excited about it. The second thing, of course, the main topic, talking about the modeling deammonification process in GPSX, and followed up with some of the model demonstration, how you can construct layouts for the deammonification process in GPSX. So we're going to give you a little bit of a demonstration with respect to that. So first of all, talking about the background of deammonification process, we are familiar with nitrification process that happens in wastewater treatment plants. The ammonia gets converted to nitrite, then to nitrate, and we also have traditional denitrification processes in which nitrates get converted to nitrite and then to NO, N2O, and finally to N2. So these processes have been historically pretty well established in wastewater treatment plants. Now, when we are doing denitrification, we also do some growth. There is a bacterial growth that is taking place, which give rise to some of the organic nitrogen, which can get converted to ammonia as well. The other process that we have is the N-fixation, which is not really important for wastewater treatment plant, but when we are talking about biological N conversion cycle, then this process needs to be displayed as well. And the most important thing, most relevant thing that we have for today's webinar is the new kind of bacteria called NMOX, which are discovered in early 1990s, and which is a pretty exciting process that they conduct in wastewater treatment plants, is conversion of nitrite to hydroxylamine, and then conversion of hydroxylamine and ammonia to hydrazine, which can get converted to nitrogen. So in this process, we don't really go through the traditional denitrification route in which we require some organic carbon. So this is a pretty exciting discovery in 1990s, and the next slide we are going to see how this can result in significant cost savings for us with respect to energy at a wastewater treatment plant when we are doing nitrogen removal cycles. So again, in a conventional nitrification, denitrification system, we have ammonia nitrogen, which gets converted into nitrite, nitrate, and both of these steps we need to have oxygen supplied to the system. When we're talking about denitrification from nitrate to nitrogen, then we need to provide some of the COD source, biodegradable COD source, which is used up in the conversion process of nitrate to nitrogen. So when we talk about NMOX biomass, which have a distinct red color associated with them, these bacteria, as described in the previous slide, can work together with ammonia and nitrite and directly lead to nitrogen production. So in this process, we can see that we don't really have to go to the second step of from nitrite to nitrate, and we can save some of the oxygen that is required in the conversion of nitrite to nitrate, and also from nitrate to nitrogen we need some of the organics, and we don't really need that in this NMOX process. Also, when we're talking about conversion of ammonia to nitrite, then since part of the ammonia is used in this reaction, we don't really have to convert all of the ammonia to nitrite, and that also leads to some oxygen reduction or some oxygen requirements that are reduced during this process itself. So if we look at the merits of NMOX process, it requires less oxygen consumption. It can save you about 60% in overall energy cost associated with oxygenation. Also, since there is no demand of the organics, these organics can be used for energy generation and not really required for denitrification process. Especially in a plants where you're carbon limited, this can come as a significant merit. Also, since these processes are autotrophic processes, the production of sludge is significantly lower than normal traditional nitrification, denitrification processes. Now, seeing all these merits, of course, and the discovery of this bacteria, the most important thing is how can we use this in wastewater treatment plants. So the initial thoughts were to use this process on the side stream deammonification, side stream removal of ammonia. For example, if we have our traditional conventional wastewater treatment plants with the scheme of primary clarifier, aeration tank, secondary clarifier, and some of the primary sludge and the secondary sludge coming to anaerobic digestion, then the supernatant coming from the dewatering system is pretty rich in ammonia, and that ammonia get recycled to the main plant. So one of the application of the NMOX process has been to remove that ammonia from the side stream using deammonification process. So what is required to do that is after the dewatering process using a nitridation reactor and then an NMOX reactor with some kind of biomass recovery options, you can build a reactor configuration or a process configuration that can utilize NMOX bacteria to directly remove ammonia from the side stream systems. This is an interesting way to remove ammonia and reduce the nitrogen load going back to the mainstream system. Another kind of a variation of the same process is doing the same thing, nitridation and NMOX in a single reactor, and that's also a feasible scheme and is an applicable scheme that has been applied to wastewater treatment plants. Now, if we look at the overall nitrogen balance in a wastewater treatment plant, then we can understand that the ammonia that we can remove or that we are removing from the side stream system normally constitute about 20 to 25% ammonia load that can be decreased from coming back to the mainstream system. But there is a 75 to 80% ammonia that flows through the main system, and the question is if we can use this deammonification process in the mainstream, then we can actually save on energy and also on some of the other aspects related to carbon requirement and sludge production. If we can achieve that goal, that is really good. So with that kind of an understanding, there have been some significant research efforts that have been undergoing to implement these processes, or at least on the pilot scale, and also taking those outputs from pilot scale and applying it in a mainstream system. So when we're talking about a mainstream system, the process scheme looks something like this. The first stage removes the carbon, and it takes away as much carbon as possible from the wastewater, recycle it to the anaerobic digestion. You can achieve higher gas productions due to higher carbon removal from the A stage and increase your gas production. Also have a side stream deammonification process, and then do a mainstream nitridation and NMOX, which is a deammonification process. So in theory, this is kind of a scheme that could work, but of course there are significant challenges in achieving this goal right now. So one of the thing also that is part of the scheme is taking part of the biomass that is grown on the side stream system to actually bio-augment the mainstream processes. So there are many different variations that are possible with respect to deammonification system in the mainstream plant. So now if we look at the process characteristics with respect to the side stream deammonification and mainstream deammonification, side stream deammonification processes, you have low flows, high ammonia concentration, most of the water is coming from anaerobic digester, which is normally maintained at 35 degrees C or a higher temperature. So there is a better control of temperature, and there is a possibility of doing a pH control because of the low flows. So that's why the side stream demonification process has been pretty well established, and it has been working in full-scale applications in many different plants throughout the world. When we come to the mainstream demonification process, we can see the contrast that we have high flows, low ammonia concentrations, and also, of course, since we are talking about a large volume of water, we don't really talk about temperature control there. There is a significant variation in the temperature. Also, there is a limited pH control that you can use on a high flows wastewater. So you can see that there is the things that can be used to run the side stream demonification process probably doesn't really work for mainstream demonification process. So there are some challenges in achieving mainstream demonification process. Now, if we talk about the technologies that are there, and this is not a comprehensive list that we have here, but these are some of the main technologies that are out there. AnitaMox, promoted by Veolia, Demon, World Water Works, Canon ANAMOX, which is a PARC system, Demon process, Purac, and Clear Green by Suez Degremont. So most of these technologies, you will see if you try to compare them, some of them are based on SBR systems, some of them are based on the attached growth systems, and some of them are based on granulation or the granular sludge type of system. So there are some differences, but ultimate goal is actually to provide stable conditions for nitritation and ANAMOX bacteria. So if we look at the key technological features that are there for these reactors, you will find one reactor or two reactor configurations. Like I said, you can have suspended biofilm or granular kind of a sludge, and the two major aspects are that we have to provide a selection process so that AOBs can outcompete NOB, and also since the ANAMOX biomass is very slow growing, we want to retain that biomass in a very, very efficient way to grow those bacteria. Now coming to our main topic is the modeling. So how do we model this deammonification process and what is needed? So if we look at the ASM family of models, which are ASM1, ASM2D, and ASM3 models, you would immediately notice that these are based on one-step nitrification process. So if we want to do deammonification process, one of the fundamental requirement is that we need to have the production of nitrite, because everything starts from nitrite in deammonification process. So we need to have a process in which we can predict how the nitrite is going to form and how it's going to be utilized. So what is needed is we have one-step nitrification, but what is needed is we need at least two-step nitrification. We saw that hydroxylamine could be an intermediate in the nitrification process, but at the minimum we need two-step nitrification, so that we can model how is the nitrite concentration in the system and how the nitrite is going to be used. Second thing you will notice in the ASM family of models is that they are based on one-step denitrification. So once we make the modification to have two-step nitrification, then we need to also change our model for denitrification and at least make it compatible with or change it in a way so that the nitrite which are being produced in the system, they can be denitrified through normal heterotrophic processes. The third major item is that there is no ANAMOX bacteria, or the growth of ANAMOX bacteria is not considered in ASM family of models. And if we want to model the ammonification process, then we need to have ANAMOX growth built into these models. So in version 6, which was released in 2011, we developed a comprehensive model which is known as MANTIS-2 model. And in this MANTIS-2 model, we implemented two-step nitrification process, two-step denitrification process, and ANAMOX growth to allow the modeling of the deammonification process. So And since it released in version 6, we have been updating this model continuously and making it compatible with the recent research that has been coming out, and trying to keep it up to date. So this model has been there since version 6. So if you have version 6, you should have access to this demodification, or the two-step nitrification, two-step denitrification anamorphs growth, which is built into Mantis 2 model. You should have access to that. So now, just to give you a little bit of a background about how do we model this two-step nitrification process, which require modeling two populations. One is ammonia oxidizing bacteria, and the second one is a nitrite oxidizing bacteria, NOBs. So if we look at the stoichiometry of these reactions, they are pretty much standard textbook stoichiometry, so I have not put that on the slide, but we are interested in what are the growth rates, or what are the growth rates of these two bacteria, and how can they compete with each other under different environmental conditions. So for ammonia oxidizing bacteria, if we look at the equation, we have the mu max, which is the maximum growth rate of the bacteria itself. Then we have the substrate, which is ammonia for the ammonia oxidizing bacteria. And also one of the requirement is that there should be some oxygen that should be present for the growth of this bacteria. So we have that particular term here saturated expressed as a monod term with respect to substrate. And then we have a number of other terms which are pretty important if you want to model side stream system. And two of them are the inhibition terms with respect to free nitrous acid and free ammonia. So these are some of the things very well detailed in literature about how free ammonia and free nitrous acid could be inhibitory to these bacteria. So we have an inhibition term for free nitrous acid, and we have a inhibitory term for free ammonia for ammonia oxidizing bacteria. Also, in addition to these two compounds, there could be a pH effect on the growth of these bacteria, and also the temperature correction factor that we take into account in the growth rate of for ammonia oxidizing bacteria. When we're talking about nitrite oxidizing bacteria, nitrite is the substrate for nitrite oxidizing bacteria. So a monod term with respect to substrate concentration. Again, NOBs require oxygen, so a monod term with respect to that. And NOBs also have their own inhibition function with respect to free nitrous acid and free ammonia, and also a dependence on pH and temperature. So if we look at how do we go about defining this, some of the kinetic coefficients that are required, for example, the growth rates, half saturation rate coefficient, inhibition coefficients. Then we did a detailed literature review and surveys to try to identify what are the values, or what should be the reasonable values of these kinetic coefficients. So this is a diagram, or these are a couple of figures which I took from one of the classic papers from Antonison, which was done in 1976. This is a very classic paper describing the inhibition of nitrification by ammonia and nitrous acid. So in their study, they did a very extensive study, experimental study, in which they tried to outline the regions in which free ammonia and free nitrous acid could affect the growth of these two bacteria. So if you look at this diagram, this is their hypothesis, in which they hypothesize that zone 1, in which there is a free ammonia inhibition to both Nitrobacter and Nitrosomonas. Zone 2, free ammonia inhibition to Nitrobacter. Zone 3, it's a complete nitrification, so no inhibition. And in zone 4, we have free ammonia, free nitrous acid inhibition to Nitrobacter. So there are these boundaries that they define, and they did experimental studies to define the values of these bounds. So if you look at this diagram here, you could see that there are some reasonable fuzziness about their boundaries, but we can see that free nitrous acid concentrations of 0.2 could be detrimental, starts detrimenting the growth of Nitrobacter. At 2.9, there is no growth of the complete Nitrobacter are completely inhibited. So on the right hand side, again on the free ammonia side, we can see that at a free ammonia concentration of about 1, probably, we will start getting into the zone of inhibition of Nitrobacter. And if we go more than 90 milligram per liter here, then we are going to get into the zone of zone 1. So there are, as you can see from the data, that there is a little bit of a band exists between the clear inhibition to kind of a minor inhibition. So there is some boundaries and there are some fuzziness with respect to where is a clear-cut values for this these inhibitions to start. So we also looked at some of the recent literature and went through some of the recent data to come up with the values of inhibition concentration of free ammonia, free nitrous acid, and free ammonia and free nitrous acid for Nitrobacters. So these are the values which are there, but of course we keep on revising our values as we get more and more information. Now coming to the pH inhibition, we compiled some information from various sources, and we can see that ammonia oxidizing bacteria, there is an optimum pH here, which is not so much different than the nitrite oxidizing bacteria. But one thing that we notice is that ammonia oxidizing bacteria have a better tolerance with lower pH, but except this particular value here, rest of the value says that they have a better tolerance to a lower pH than nitrite oxidizing bacteria. So we can use this as a reference and try to define a model with respect to pH inhibition function. And the model that we use inside GPSX is a pretty simplified model, but it's pretty much very easy to understand. The only thing that we need from to define the model values is the 50% inhibition on a lower range and 50% inhibition on the higher range of pH. And once we get those two values, we can have some kind of a linear relationship up to the optimum activity. And this is a kind of a simplified model, but works well with respect to the understanding of the 50% inhibition values that can be determined from experimental work. So we use this model, and the equation that we use inside GPSX is shown here. I'm not going to go into the details, but we can determine this factor based on the 50% inhibition values on the lower pH range and the higher range, and from there we can find out those values and use them into kinetic expressions. The third important thing is the temperature and how it affects the AOB and the NOB growth rates. And this is again one of the classic examples coming out from Delft University, in which they use this temperature as one of the principle in achieving nitridation for the Sharon process. And in this particular case, from this diagram, as you can see, that the ammonia oxidizing bacteria is at a higher temperature, has a higher growth rate, and NOBs have a lower growth rate. And so if you have higher temperatures, then it is probably easier to control or outcompete NOBs just by controlling the SRT in the system. So this kind of kinetic, this kind of relationship is built into the AOB and NOB kinetics in the GPSX. Now coming to the NMOX stoichiometrics and kinetics, and again we are again using one of the the first one, the stoichiometry proposed by Strauss for NMOX bacteria, in which it is proposed that 1 mole of nitrogen reacts with 1.32 mole of nitrite, and it produces 1.02 mole of nitrogen here, and there is some production of nitrite. So if we see 1.32 and 1, which is 2.32, so there is a 10% nitrite that is produced from this reaction. And we can also notice that there is a little bit of higher nitrite nitrogen concentration necessary than the ammonia concentration for this reaction to be most efficient. The kinetic expression that we use is a pretty simple kinetic expression. Maximum growth rate of NMOX biomass, the monode kinetic with respect to ammonia, and monod expression with respect to nitrite concentration and inhibition to the oxygen concentration. And also we have the pH and the temperature correction factors built into this equation. So again, the kinetic coefficient that we have for the NMOX reaction, we again went through a large set of literature values, compared those values, and came to some of the values or selected some values for the kinetic model for the NMOX in GPSX. Now you can see that when we are talking about deammonification process, we are talking about three main bacterial species. One is the AOBs, NOBs, and NMOX bacteria, and we are trying to look at ways to prevent the growth of NOBs and try to increase the growth of NMOX. So, and we can see that all these bacteria depend on the environmental, their growth rate depends on environmental conditions, which can depend on the DO, pH of the system, temperature, SRT, free ammonia inhibition, free nitrous acid inhibition, and also depending on physical selection, because depending on what kind of a selective washout you have, selective augmentation. So there are several parameters that are needed or that needs to be considered while going in the process planning or process development for this kind of system. So it becomes almost like a multi-parameter optimization problem, and probably using a modeling approach is one of the most important aspect maybe that should be applied for process design or process studies and process optimization here. So when we are talking about multi-parameter optimization, of course our goal is to let the AOBs grow and produce nitrite nitrogen, and once the nitrite nitrogen is there, then of course we know that there are three bacteria that want to utilize this: NOBs, NMOX, OHOs, which is ordinary heterotroph organism, and of course they utilize this in a little bit of different environmental situations. So our goal is to provide those environmental conditions which can actually prevent the growth of NOBs and prevent the growth of OHOs, so that most of the nitrite nitrogen can be channeled to NMOX bacteria. So this is our goal, and as you can see that there are several number of parameters that you need to play around to achieve this particular goal. So with this, I hope I have given you enough background and modeling principles with respect to these three key bacteria. I would like to hand it over to Spencer to show you a little bit of a couple of demonstrations of some of the plans that you can build in GPSX to study your deammonification process.
Thank you, Rajiv. So I'm going to cut away from the slides and bring up my copy of GPSX, and I'm going to demonstrate side stream deammonification here under two different arrangements. And so these are corresponding to two of the examples that Rajiv gave earlier. So in this particular case, I'm just going to quickly explain. This is a conventional activated sludge plant. We're modeling it in the comprehensive library using our Mantis 2 model. As Rajiv said, we need to use this model, our most comprehensive model, because it has the two-step nitrification and denitrification, and it also has the NMOX bacteria type. So this conventional activated sludge fully nitrifying plant up here, we're taking the solids to anaerobic digestion and then some dewatering, and this is the side stream treatment process down here. And the way that I've got this set up for this particular example is to have a single aeration basin here that's doing just nitritation, taking that ammonia to nitrite, and then the NMOX tank, which of course is not aerated. And then there's some solid separation here with the recycle to maintain and keep those NMOX. In this particular case, we would be probably a situation where they would be growing granules that would be able to be preferentially separated out from all of the other biomass and retained at a higher concentration. So let's bring this over here, and I'm going to run a steady state simulation. And well, we're waiting for that to happen here. I'll just mention quickly these input parameters and look at the kinetic menu here. Rajiv was just describing the various kinetics that we use to model the different biomass types. So if you slide down the kinetic menu here, you'll see that we have the various growth rates and half-rat saturation coefficients and inhibition terms. If we slide down here, we can see them for the AOBs, the ammonia oxidizing biomass, and nitrite oxidizing biomass for the NOBs here. We can see their relative growth rates here, 0.9 and 1 for AOBs and NOBs respectively. If we slide farther down the menu here, we can see the part of the menu for Anammox biomass. And so those were 0.9 and 1. We can see here that maximum growth rate of Anammox bacteria is 0.018. So it is quite a lot lower. And as Rajiv mentioned several times, this is a very slow growing biomass, which you want to go to extra lengths to be able to grow and maintain in your system. Okay, so let's take a look at the results just as a simple steady state solution here. And I'm going to start by looking at that nitritation reactor here. And what we're looking at is coming into this tank. This is leaving our dewatering unit. The ammonia coming into the tank, and this column here is 350 milligrams per liter of ammonia and basically no nitrite or nitrate at all. And then in this tank, there's no recycle here. So this is a condition where the HRT and the SRT are the same. It's a flow-through tank. And if I look at the HRT here, I'm going to flip this over to days. It's about 1.3 days. So we are hoping to take this to some partial nitritation here. So, and that's indeed what is happening. We're maintaining some aeration in this particular tank. The ammonia is being reduced by about half. Down to 162, and we are generating nitrite, but not any significant amount of nitrate. So I've set this up so that it's the right amount of nitritation here to get that kind of balance. Then that goes into the Anammox reactor. So let's take a look at that one. Anammox reactor is here. So those concentrations that I just mentioned, ammonia and nitrite and no nitrate coming in. And then we are growing the Anammox biomass in this particular case. We can see the ammonia being reduced as it goes through. We can see that nitrite being reduced. And as we mentioned on the previous slide about the stoichiometry here, we can see we're actually generating some nitrate. So, and it's in a roughly sort of 10% kind of number as we're reducing down that ammonia. So that's a sort of a good example of how you can see that arranging these particular tanks in order to be able to achieve a certain set of environmental conditions can promote the growth of Anammox. And in fact, you can even plot how much Anammox bacteria is available by going to your state variable menu and plotting the concentrations of the individual biomass types. So let's take a look down here. This is the section that shows us the various biomass types. And if I go under the More button here, the Anammox is right at the very end of the list here, and we can see that we're growing relatively significant number for especially a slow-growing biomass. So these are being captured here in this solid separation unit and then being recycled back in again. And that's actually a really key factor. So to show you the sensitivity of the model here, I'm going to adjust the removal efficiency, or that capture fraction of the Anammox bacteria. It's a really key factor. Right now we're capturing 95% of the Anammox that comes out, and we're recycling it back in. This is reflective of technologies where you can settle out those Anammox granules. So if this was not the case, if we weren't doing a very good job, and let's say we're going to knock that back to 80%, we're going to make it so that it's not preferentially, it's just going to be captured the same as all of the other types of biomass here. And I run that situation again. We can see that we have lost our Anammox biomass. Now we're saying we're not basically removing any ammonia at all. And so our ammonia and our nitrate are basically the same, floating all the way through. So this is a key thing here, and you can see the relative importance of being able to capture that, capture those Anammox granules properly. Okay, so that's doing side stream with two separate tanks and doing a capture of that granules. What I'm going to do is show you another one, which is the biofilm type approach. So let me explain that. This is exactly the same layout that I just had previously with the digester dewatering, and instead of 2 tanks, we're doing it all together in 1 tank here. This is reflective of the AnitaMox technology, where we have plastic carriers that are present here, and then these are used to grow both the AOBs, and hopefully we'll be suppressing the NOBs, and then also the Anammox bacteria. They're all going to grow together in that same biofilm. So I would like to just briefly mention here some of the features of that. This is our hybrid model. This is just our regular model. It's the same unit process that you would use to do IFAS or MBBR, and in this case we're doing an BBR type of configuration, one flow through. You specify the reactor portion that's filled by the media and the media specific surface area and so on. So I've run that example there, and we can see that in this AnitaMox reactor here, again, that same ammonia, the 350 milligrams per liter, same as we had in the previous example, is coming in, and all of that ammonia and the nitrate is being removed fairly efficiently in this particular case. Now, of course, because this is a fixed growth type system, all of that stuff is being retained in the tank. So we're getting, we don't have to worry about capture and recycling back our Anammox bugs, and we're generating a little bit of nitrate. So now the key here, and you can investigate what's going on very nicely by looking at the profiles of the various concentrations in the biofilm, and these are things that you can plot directly in GPSX. So I'm going to blow up this biofilm, and now the bar at the front, this concentration at the front, is what is present in the liquid, in the bulk liquid, and for now we've set our aeration such that we're getting about 0.25 milligrams per liter of oxygen. And then as we can see, as it diffuses into the biofilm, this layer right here is the one that's next to the liquid, and as we go farther back, this is the one at the back here is the biofilm layer that's attached to the media. So as you would expect, of course, if we're aerating the liquid on the outside, then we would see a gradient going back, and we can see that it decreases as we go back. And there's lots of anoxic zone back here for our Anammox bugs to grow in. So, and in fact, we can actually plot the Anammox biomass concentrations here. We can see there's, of course, very little in the liquid, but they're all together here in those biofilm layers. And we can see that we've got some AOBs up front here, right up next to where next to where all the good oxygen is there. And we have successfully suppressed the NOBs here. We don't have enough oxygen for those to grow. So we're able to sort of keep an eye on, the relative concentrations and also the relative location of where all of these different things are growing in our biomass. So just to give you another different example of what happens here, again, this is a key feature here of doing this in a biofilm context, is to make sure that you're not over aerating. Right now we're having enough to do the AOBs to get that to that nitrate step, but not so much that we're going to have a fully aerated biofilm. If we did that, for example, if I ran this system with a DO set point of 1.5 milligrams per liter instead of 0.25, and I'm going to run this simulation again, we'll see here, if I look at that oxygen again, 1.5 here out in the liquid, and we got lots of oxygen all the way fully penetrating through that biofilm. Well, of course, that means that we have no Anammox here. This is all zero, basically. And we do have NOBs because we haven't, successfully suppressed them anymore. And if you'll notice here now, our ammonia and nitrate and our nitrite concentrations are low, but we have lots of nitrate. What's happening is, of course, now we've gotten to a position where we're fully nitrifying all the way over, and we're not getting that Anammox treatment anymore. So this is a good example of how you can use a model to find that right system point, to find the point where you've got the right environmental conditions to grow the right kind of bacteria that you want. Okay, so let's go back to our slides again here. And with a few final thoughts about this, as Rajiv mentioned, there's really significant benefits to using autotrophic deammonification processes. Certainly one of them being that you don't have to supply nearly as much oxygen. You're not taking it all the way to nitrate. You're not even getting rid of all of the ammonia. And there are a number of side stream deammonification systems that are pretty well established in our industry, and lots of full-scale installations out there. However, mainstream deammonification, where you're doing that right in the main liquid train, is also something that people are working towards, and there's quite a bit of research going on in this area and piloting, and I was attending a conference earlier this year in Washington where I got to hear about various plants that are working their way towards being able to achieve this in a mainstream full-scale system. The model of structure in GPSX is there, and it's well calibrated, and we've put it together to allow you to be able to investigate different types of dehumidification systems and experiment with those and try to optimize them for systems that you may want to model. And these parts of our models in GPSX are always undergoing continuous improvements as we learn more about those processes, about those bacteria types, and we update our kinetics and update the structure and stoichiometry of our models as well.